Hi everyone. In this video we're going to be talking about the chain rule for derivatives. So to start, I've got a little visual investigation for you just to motivate why the rule exists and is the way it is. So either pull out your calculator or at least follow along with mine, and we're going to graph the function y equals sine of 2x. And I'm also going to have you change the viewing window a little bit just to make the function a lot bigger so we can see it. So again, sine of 2x. And then notice we're going to change viewing window so we get one full period. Oh, that would be two full periods. Math is hard. And we're going to make the y values -2 to +2. So there we go. 2 periods. And then you'll notice I've already changed the sign windows, or the viewing window as well. And so my question for you is, what do you think the derivative of this function is? What do you think the derivative of y equals sine 2x is? So what most people guess is they say, well, the derivative of sine is cosine, so why don't we just try this? The derivative of sine 2x would be cosine of 2x. Let's try that. So let's also graph that. Nope. Hello? Hello? Jeez. Stop. Just work. Could you just work? I'm not clicking 20 times. I'm clicking once. Thank you. All right. So there's what we think the derivative is. And then I'm also going to punch in, stop. I'm also going to punch in the derivative notation of the function we started with. And let's just look at what the graph looks like. So I'll turn that on. Check. And escape. Oh. Huh. So the black function on here is the one that is actually the derivative. The red one was the one that I guessed, and remember the blue one is the original function. So compare here. They have the same x-intercepts, but the black one is a lot taller. In fact, it's twice as tall. So couldn't we fix up our guess by multiplying it by 2? So that would make our derivative 2 cosine of 2x. And if you don't believe me, let's just graph that real quick. So fourth function, 2 times cosine 2, get out of here, x. Aha, and the pink overlaid the black, so we know we've got it correct. So, so what do you notice about this? Well, to get the derivative of this function that I circled 100 times all the way up here, not only did we have to take the derivative of the sine part, we also kind of have to take the derivative of this little 2x bit on the inside, because the derivative of 2x gives us that 2. This leads us to the chain rule. So here's how the chain rule is printed in the book. It says, suppose you have a function y equals a function of u, where then u is a kind of second function. The derivative is the derivative of the outside part times the derivative of the inside part. I think this is really weird notation. I prefer to notate it this way. So if you don't like that, think about it like this. Suppose we have a function y equals, I don't know, how about f of g of x? So a composite function like you would have worked with in Algebra 2 last year. The derivative then is the derivative of the outside function, so the f, keeping the inside the same, kind of like we did with the 2x, right? So it was still cosine of 2x times the derivative of the inside function. And I like this because then you can repeat it. So if there's 3 functions composed in each other, you can still do it. 4, whatever. I mean, I don't know if we'll ever hit 4. But I think this is a little bit easier, but I wanted to print for you what is in the book. So let's work a couple examples here. Our first function is y equals the tangent of 2x. So our derivative, y prime, would be, first, I would consider the tangent to be the outside function. So the derivative of tangent is secant squared. Keep the inside the same. Then chain rule, multiply by the derivative of the inside, which is 2. As you get better with this, you'll see it more right away, and you can just put the things that are constant multiples out front. You certainly don't have to, though. It would have been just fine for now if you want to leave it as secant squared of 2x times 2. All right, so for our next one, you might think that doesn't really look like a function inside of another one, but consider it this way. If the outer function was just f of x equals x to the 6, and the inner function is the 4x plus 5, now hopefully you can see how this really is a situation where it's f of g of x. So let's take the derivative out here. So the derivative of the outside function, let's see, that would be just a power rule. So I'll bring the exponent down. I will keep the inside the same, subtract 1 from the exponent. And then to finish off the chain rule, make sure we multiply by the derivative of the inside, which 4x plus 5, the derivative there would just be 4. Similar logic on number 3. We can say the outside function is the square root, and the inside function is the 5x minus 7. So the derivative then would be, now let's flip this so it's exponential. Let's bring down the exponent so we can use the power rule. Keep the inside the same, subtract 1 from the exponent, and then to finish, make sure you multiply by the derivative of the inside. Still works, even if we've got a negative exponent here. Let's bring down the exponent, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside. So let's see. Again, we got another power rule here. Nope, no x, just 12. Where's my eraser? There it is. Boom. Let's turn the page. Okay, so I've got a couple more complex examples for you here. Let's look at this first one here. Well, there's actually 4 things going on here, because you could rewrite that function as quantity sine of 3x plus 2 all to the 4th power, right? So really, it's kind of like we have the old f of g of h of x scenario. Yeah, that's right. 3 functions all nested. So our innermost function would be the 3x plus 2. The kind of second level function would be the sine of just, the stuff that's inside it. And then the outermost function would be all the stuff to the 4th, if we were building a composite function like this to create that. So the good news is the chain rule just basically keeps repeating over and over and over again. So, well, I'll just show you what I mean. So as always, it's derivative of the outside. So let's bring down the 4 for the power rule, keep the inside the same. Let's subtract 1 from the exponent to finish the power rule. Then the rule is derivative of the inside, which, the derivative of the inside is still a chain rule problem. So the derivative of sine is cosine. Keep the inside the same. And now, finish off that chain rule times the derivative of the inside. Wasn't that wonderful? Problem B is similar. It's another one where you got 3 functions listed inside themselves. So you've really got everything to the 1/2 power. Inside that you have the cosecant function, and inside that further you have the x squared. So the derivative would also be kind of a triple function chain rule. Let's start with the outermost part. Let's bring down the 1/2. Keep the inside the same. Then finish off the power rule. Now the chain rule would tell us times derivative of the inside. So let's take the derivative there. Let's see. The derivative of cosecant is negative cosecant. Keep the inside the same. Cotangent. Keep the inside the same. And then to finish off the chain rule, it'd be times the derivative of the inside, which would be 2x. So both of these are, I don't know, I've always called them triple chain rules, but I guess we only really have to use the chain rule twice. How about they're made of 3 functions? So you have to extend the chain rule. All right, let's look at the next one. So for C, you'll notice we have a fraction, so we're definitely going to have to use the quotient rule. And in the numerator, we have one of these nested functions, so inside the quotient rule, we're going to have to do a chain rule. So let's see, quotient rule it up, low, times derivative of the high function. So here comes our chain rule. Let's do the derivative of the outside function. So sine becomes cosine. Keep the inside the same. Times derivative of the inside. So that's our derivative of the high minus high d low. So let's see, power rule here. Strike a line, square below. Whoops, that's going to be minus 7. So on the surface, it looks bad, but just take your time, talk yourself through them. I think you'll find they're actually not terrible. The only really terrible ones are these ones where you keep deriving over and over again, like A and B on this page. Let's look at the last one on this page here. So the first thing that comes to my mind is that it's negative cosecant squared. You can think of this like it is negative 1 times, and then just so that way it appears like a chain rule problem, I'm just going to write it as cosecant of 3x minus 1 quantity squared. So this might be another kind of triple function chain rule problem, right? Because we have the squared all the way on the outside, then we have the cosecant in the middle, and on the inside we have the 3x minus 1. So let's derive, let's just bring the constant multiple along for the ride. So we'll take the entire rest of our answer and just multiply it by negative 1. And then let's start deriving this stuff. So let's see, we'll start off with the power rule. We'll bring down the 2, and now we're chain ruling. So I'm going to keep the inside the same. Cosecant 3x minus 1. Whoa, 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 whoa. Okay, and that's going to get really annoying if that keeps happening. Okay, let's see if I fixed it. The exponent was 2. We brought it down. The remaining exponent would be 1. We don't really need to write an exponent of 1. Next up, let's do the derivative of the inside. So this time it would be the derivative of cosecant 3x minus 1. So the derivative of cosecant is negative cosecant, same inside, cotangent, same inside. And then finally, let's do the derivative of the very inside thing, the 3x minus 1, which would just be 3. And then again, this minus 1 applies to all of it. I guess I do see 2 minuses here. Got 1 here, got 1 there. So they would cancel each other out. If we really wanted, we could combine this. And I see a pair of cosecants here. So you don't always have, typically we'll only put these together if we actually have to do some solving, but let's just make it look pretty because we can. So I got my 2 cosecants, put them together, and then the cotangent, 3x minus 1. All right, let's turn the page. So I got two last ones here for you, and you actually don't have to be alarmed that the page is otherwise blank. Basically, as always, well, okay, we don't do this every video, but I'd like for you to try these yourself. And don't worry, there's plenty of space for you to write down the correct way to do them if you make a mistake, not that I think you will. So yeah, just pause the video, try and take the derivative of both of these functions. And here we go, here's what they look like. So for the first one, the first thing you had to do is use the power rule to bring down the -2. Keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside. The derivative of something linear is a constant. And then make sure you change this to exponential form, so it's really x to the 1/2. So when you derive it, bring the exponent down, subtract 1 from the exponent. That's all there was to it. For b, we had a product rule with nested chain rules inside each of the two little things. So I tried to write it out using our little sing-songy thing below, dfg plus fdg. So the derivative of f would have been power rule, bring down the 2, keep the inside the same, times derivative of the inside because chain rule. And then g, so I just copied g, plus copied f times the derivative of g. So again, power rule, bring down the -3, keep the inside the same, subtract 1 from the exponent. Then to finish the chain rule, multiply by the derivative of the inside. All right, good stuff. I will see you tomorrow.